Okay, hello everyone. So in this session, I want to solve another example on linear momentum or thrust and trying to find the forces that act on this object, the anchoring forces to use by using the linear momentum equation, okay? So the question is as follows. Estimate the nominal anchoring force for which to design. Okay, so here we have this system where it takes air from here, and then it has an intake air from here in section 1, and then we have a kind of exhaust at the end where it releases the air to the atmosphere, okay? So the problem gives us the area at the intake, which is 1 meter per 1 meter square. So here we have the area. And then the intake air velocity is 200 meter per second. This is also given. And exhaust velocity is given as 500 meter per second. And then this is the geometry of the problem that we have, that is shown here. And then also the intake pressure is given to us, the both static, which is the gauge pressure, and also the absolute pressure is given for intake, and also the exhaust pressure is also given. As you see, the static one or the gauge pressure is 0, meaning that this is in the vicinity of the atmosphere. Once the air comes here, is in the vicinity of the atmosphere, okay? So now we want to estimate the nominal force that this system kind of exerts on this, say, the structure here, right? The structure that we want to kind of design here, okay? How much force, anchoring force, is required to keep this kind of system in place and doesn't let it to kind of move, okay? Let me now get started. So again, when you want to find the forces and these kind of structures, the first thing we want to do is we want to kind of draw a proper control volume, okay? And here the control volume is fairly easy because we have the information about section 1. So I want to start it from here. Let me try it again with another color. So I start from section 1, fixed control volume in space. And then it also crosses section 2 here. Okay, so this is my CV, control volume. And now the other thing I want to do is to draw the coordinate system. So this is the coordinate system I have. This is in the z direction, and this is going to be in the x direction. And after that, I want to draw the forces or free body diagram that the forces that act on this control volume, okay? So what do we have? First of all, we have pressure at A, so I'm going to write it as P1. A1. And then we have pressure at section 2, which acts as P2. A2. And then we have velocity. So here we have velocity of U1. And then we have a larger velocity at the exhaust as U2. And what else do we have? The other force that acts is the force that this acts on the anchoring force, which I show it as FH, F horizontal. Okay, so this is going to be my free body diagram. Okay, so now the next thing I want to do is to write the momentum equation. In x direction. Again, this is a steady flow, so we are going to use this formula here. So let me just copy it. You notice, so I just clean that. So the integral of u rho v dot n dA over the control surface equals to the sum of the forces. So for the forces, for the pressure, we have both static, which is the gauge pressure, and also the absolute pressure. Okay, so what I want to do here in these problems is always I want to use the gauge pressure. And what's the reason for that? And the reason is because the atmospheric pressure is kind of exists everywhere, right? So if I have like if I want to kind of also consider the atmospheric pressure, it acts everywhere. And this is gonna cancel out, right? When you do your calculations in this control volume, this is gonna cancel out because this exists everywhere. So I just wanna ignore that and neglect that and only look at the gauge pressure, which is kind of important for us. Because the atmospheric pressure, we are all in the atmosphere, so the atmospheric pressure kind of puts pressure on all parts of us, and it's only a function of height. And because the height of the difference in the height of all the objects that we are considering is small, it's not going to change that much. So the atmospheric pressure between here and here is almost equal, right? The difference is very small. So that's why, because the atmospheric pressure is almost the same everywhere, and it acts on all the elements everywhere, we just neglect that. Okay, so we have to write everything in terms of the gauge pressure or static pressure. So the way I want to write it down is as follows. So for P1, if P1 is the absolute pressure, let's say this is absolute, or let me just write it down. If P1 is absolute, what I want to do is to subtract the atmospheric pressure from that to get the static pressure, okay? So the way I'm gonna do it is as follows. So I just write it as P1 minus P atmosphere, which is atmospheric pressure, times A1, this is in the positive direction. And then we have also the horizontal anchoring force, which is in the positive direction. So I write it as FH plus FH. And then we have the other pressure force, which is in the negative direction with respect to X. So I write it as P2. Again, I have to subtract the atmospheric pressure. If this is not the gauge pressure, it's the absolute pressure. P2 minus P atmosphere times A2. And this is how I should write this down, okay? So this is gonna give me P2 gauge, or you can say the static pressure. This one is also like that, P1 gauge, okay? So now let's look at this term. Again, this term, as I said, you can just remember the alternate forms of that. And I'm going to use this one because this one is the easier one, which is the definition based on the mass flow rate. Okay, so let's look at that here. So the first term is U1. First, we have to multiply U by the m dot. Well, U1 is in the positive direction, right? So I write it as plus U1. And now the other thing I have to be careful about is m.1, which is the mass flow rate. So is the mass going into the control volume or is it going out of the control volume? As you see, it's going into the control volume, right? And as we said, based on the convention we had, if the mass goes into the control volume, that means that, and because n vector is always outward of the control volume, is defined outward based on the convention that we made. So this means that then the sign of the inflow should be always negative. So I just write it as minus m.1 plus the second term, which is going to be U2. U2 again is in the positive direction, so I write it as plus U2. And do we have an inflow or an outflow? As you see, we have an outflow, so I write it as plus m.2 equals to P1 gauge times A1 minus P2 gauge times A2 plus F horizontal. Okay, so now I have m.1 and m.2. I use conservation of mass. This is a typical approach that we use here because we have two m dots and we want to only have one. So m dot, which is the mass flow rate in the whole system, equals to m.1 equals to rho, the m dot, the definition of m dot is rho q, which is going to be rho A1, rho 1, A1, U1. So this is the definition we had before too. You can look at it here, right? Rho A1, V1 equals to m.2 equals to rho 2 A2 U2. So just one thing that you need to be careful about, because here we have air, we don't have water, right? So the density in air can significantly change based on the pressure and the temperature. So that's why we should be careful to have two different rhos, because rho is not constant here. But in water, you can simply, most of the time, you can assume the density is not changing in these kind of problems that we are kind of dealing with, okay? So, assuming for this and factoring out m dot in the equation, original equation, will lead to m dot times u2 minus u1 equals to, again, P1 gauge A1 minus P2 gauge A2 plus FH, or let me write it as just P1G so you understand it. This means gauge. P1G A1 minus P2G A2 plus FH. And so now in order to find m dot, I have the intake velocity and also have A1, right? And the only unknown is rho 1, right? So let's see, the question is what is m dot 1? So in order to find that, we need to find rho 1, need to find rho 1. So rho 1 we can use ideal gas law, so it's P1 over R. And one thing I think I forgot to write is that the intake temperature is 268 Kelvin. Okay, so this is also another thing. So we have P1 over RT1. So this is ideal gas law, which equals to, what is P1? It is, and one thing we need to be careful when you write down the ideal gas law, this is absolute pressure. This always has to be absolute pressure because the ideal gas law is constructed using the absolute pressure and for an ideal gas, and it's not the gauge pressure. So you have to be very careful here. Be careful about this absolute pressure. So let me show it with another color so you better remember it. Absolute. So what is the absolute pressure of intake? It is 78.5 kilopascal. So I just write it down, 78.5 kilopascal. And then to convert it to Pascal, I just need to divide multiply it by 1000, and then over R, the constant of gas is 286.9 joule per kilogram Kelvin, and then times T1, which is what it is 268 Kelvin. And if you calculate it, it's going to be 102 kilogram per meter cube. Okay. So now we have this, and I can now calculate m dot. So m dot is going to be what? Rho 1 A1 U1. So rho 1 A1 U1, which is 1.02 kilogram per meter cube. A1 is 1 meter square, and then U1 is given also 200 meter per second. which gives me 204 kilogram per second. This is the mass flow rate that we have in this system. And so now that I have m dot, I can calculate the horizontal anchoring force, which is gonna be FH. So first of all, I have m dot times u2 minus u1, so I have 204 kilogram per second. u2 minus u1, u2 is 500 meter per second and u1 is 200 meter per second, so I just write it down. Minus 200 meter per second. Then I have what? I have plus P2 gauge A2. What is the P2? P2 gauge is the static pressure at exhaust, which is what? Or the gauge pressure at exhaust, which is 0. So I just write it down as 0 times A2, and that's why we didn't have A2, and this was a trick because it was actually, the pressure was 0, so we didn't really need that. And then we have minus, so these all go to the left-hand side, right? So that's why I have minus here. So I have minus P1G times A1. What is P1G? The gauge pressure of 1 is minus 22.5 kilopascal. So I have minus 22.5 kilopascal times 1 meter square. And if you calculate all of this, it's gonna give us 83,700 Newton. So it's a large force that is applied to this, the anchoring force that needs to take this system into place, right? So this is how you can actually solve this kind of problem. It's pretty straightforward. You need to first, again, draw control volume, write the momentum equation, and in this form use this mass flow rate to be easy based on inflow and outflow and the directions, and write the sum of the forces that you have in the system, and then use the conservation of mass to find another additional relation between the m.1 and m.2, the inflow and outflow in the system. And finally, if you have air, you can use ideal gas law. Otherwise, water, we don't have that, so we might need to find other relations, or sometimes the problem gives us more information. Okay, so this is the general approach for that. And now let me talk about another topic, and this will be the end of the linear momentum equation. And after that, we will go to I will drive the energy equation. And based on the energy equation, we can derive the Bernoulli again, because that's going to be the mechanical energy. And that will be the end of this chapter and part of the course. Okay, so let me now start a new topic, which is linear momentum equation for non-uniform pressure distribution. So far, the pressures that we investigated were all uniform, right? So we didn't have, the pressure was kind of not changing across this kind of cross section, and it was not also changing here The same for the other problems that we had. The pressure was not changing along this cross section and this cross section. We had a constant pressure, or kind of we can say an average pressure, P1 or P2, okay? But what if the pressure is also changing in the controlled volume that you are investigating, okay? So one example is shown here. So what if you have these, for example, slice gate, and then you want to write the kind of the momentum equation in this slice gate scenario, okay? So the CV that you have selected is something like this. This is the control volume because you have the velocity here, and then what if you have this? What should you do? Because the pressure, as you know, for this control volume here, for this side of that, is gonna be hydrostatic and is variable, is varying in depth. The same thing for here. So how we are gonna approach this is pretty simple. We just need to account for that distribution as well, okay? So the way we are gonna do, again, we first draw the control volume that we have. So this is the control volume that we have. And then in the free body diagram, we have to account for that hydrostatic pressure distribution. So the pressure that is applied here, the pressure force is going to be something like this, right? So it's like a triangle. The same thing for here is like a triangle. So we account for that, and then what we are going to do, we can actually assume total force in the system, which is going to be like, for this one is going to be, if you have rho g h here, so if this is h, so here you have rho g h, right? The pressure at this point is rho g h. And then the pressure at here is 0, so the sum of the forces here is going to be 1/2 rho g h, which is shown here. And then this is going to be the average of the pressure force times h, right? So 1/2 rho g h times h is going to be the force, the sum of the forces on that slice. So let me show it again for more clarity. I will draw it again here. So say here you have h, so this is h, so the pressure at here is going to be what? Is going to be rho g h, right? And then you have a triangle, right? So these are the forces, the hydrostatic pressure. So what is going to be the area of this triangle? The area of this triangle is going to be 1/2, if this is say A and this is B, 1/2 A times B, right? This is going to be the area, which is going to be the sum of the forces, the integral of the forces, which will be 1/2 of rho g h times B, right? Which is h. So let me again to make it a little bit different so you don't confuse it. This is like M and this is N, okay? 1/2 Mn, so it's going to be M is rho g h and N is h. So this is going to be the sum of the forces, okay, in this area. And if this has a width of B, say like this is extended in 3 dimensions as B, so if you have these forces along this, let's say, let me do it this way. If you have these forces like this, you also have like this force here. So you have to also multiply that by B to get the total force that acts on that side of the control volume, right? So then we have to multiply that by B to get the total force. Okay, so that's what I have done here. 1/2 rho GH times HB. Okay, so this is gonna give me the total force on that side, and the same thing for this side. We have small b, we have small h here now, rather than the big h. So if this is small h, you will do something similar to that, okay, which is shown here on the right. So this is the sum of the forces. This is the only thing you need to account for when you are kind of writing these kind of equations for these type of problems. Okay, so let me delete that. Yeah, let me put it here. So okay, so let's now write the momentum equation for this one. So momentum equation in x direction. Momentum equation in x direction is going to be the integral over the control surface of u rho v dot n dA equals to, now the sum of the forces that we had again, so this is in the positive direction. If we have this, if our coordinate system is like this, again, this is x and this is z. So we have 1/2 in the x direction is going to be 1/2 rho g h square b minus rx. Rx is the force that is kind of exerted on this control volume, say by this slice gate. And then we also have the frictional force at the bottom, right? So minus FF, frictional force, and then minus this pressure at the right, which is going to be P times A, which is gives me 1/2 rho g h square b, right? And so this equals to, if you have uniform velocity distribution, so this is an additional kind of assumption. So you can write this as u1 times rho minus, because it's an inflow, it's going to be minus u1 times A, right? This is rho AV, right? So what is A? Is going to be H times B, and V is U1, and it's negative because it's in the, it's inflow. And then we have plus, and this is plus U1, U2 times rho, and then we have again plus U2, because this is outflow, it's going to be plus, so plus U2 HB, which is AV actually, like before. And so this is going to give me the kind of the distribution, the momentum equation. Okay, so now if H So if H, big H is much greater than small h, that is something similar that we assume in slice cases. So we can assume that U1 is going to be much smaller than U2, right? Based on the continuity equation. Again, how? Because based on continuity equation, you can say the mass flow rate is constant, and because density is, for example, for water is not changing here, so I can just say volume flow rate is constant, so I can just say that A times V is going to be constant. What is A times V? A times V is going to be H times B, H times HB times U1 equals to small h times B U2, right? And B is going to cancel out. And because H is much greater than, big H is much greater than small h, so if I write this as H, let's say like this, if I write this as H over H equals to U1 over U2. So this means because this is very small, small h over is very small, so this is going to be very much smaller than 1. So U1 is going to be much smaller than U2, right? So this is how you can get it from the, you can get this from the continuity equation. Okay, now let me write this as follows. If we have this assumption, then I can write the anchoring force here, Rx, is gonna be 1/2 rho g h square b minus, and what I'm gonna do is I want to factor this out. So what I have is 1/2 rho g b h square minus h small h square minus the frictional forces that act on the bottom minus rho u2 square h times b. Okay, so this is gonna be the force that acts on this slice gate here. Okay, this is very important, right? And this is how we can simply calculate it with these linear momentum equation and continuity, right? So this is very important concept that you need to be familiar with, because this is going to help you a lot in designing these kind of structures when you want to see what is the force that acts on these kind of slice cases. Okay, slice gate. So again, this is just a final linear momentum equation for non-uniform flow. So the way you should deal with it is simple. You just need to, again, draw the same approach, draw the control volume, and then draw the free body diagram of the forces. So the only difference here is that you may need to be careful about calculating the hydrostatic forces because they are non-uniform unlike before. So it has just a little bit nuances about these calculating these forces, and other than that the approach is very similar to before. Thank you very much, everyone.